How many of you use spectacles for reading? Do you think the glass used in the spectacles is just normal glass? To find out, just remove your glass and feel the surface. You'll notice the thickness of the glass is not uniform. It may be thicker at the ends or thicker in the middle. Let us take one more example. You must have heard of a magnifying glass. Is it a special type of glass? In the examples we discussed, the glass used is called a lens. We have already seen that light changes its path when it travels from one medium to another. In this lesson, we'll find out what happens when light ray passes through a lens. First of all, let us define a lens. A transparent material which is bound by one or two spherical surfaces is called a lens. If the spherical surfaces are bulged outwards, it is called a convex lens, whereas if the spherical surfaces are curved inwards, it is called a concave lens. The best way to understand the bending of light when it passes through lenses is through ray diagrams. But before we move on to ray diagrams, first let's get acquainted with the basic terms involved in lenses.
Shown in the diagram is a convex lens. First, let us mark the points. The center of curvature for this bulging surface is marked here, denoted by C1. The center of curvature for this bulging surface is denoted as C2. The point exactly at the center of the lens is called the optical center, and this point is denoted by O. The point exactly midway between the center of curvature and the optical center is the principal focus, and it is marked as f1 for this side and f2 for this side. The effective diameter of the circular outline of the lens is called its aperture. Once we are clear with this, let us start afresh and see the basic construction of ray diagrams for both the lenses. When a parallel ray of light falls on a convex lens, the light ray after refraction passes through the focus. Let us see how this happens. Let us first draw a magnified diagram of our lens. We have learned that when a light ray travels from a rarer medium to a denser medium, the light ray bends towards the normal. And when it travels from denser medium to a rarer medium, the light ray bends away from normal. Thus we can see that a parallel ray of light after refraction from the lens refracts in such a way and passes through the focus. Since all the rays falling parallel on the lens are going to converge at the focus, a convex lens is also called as a converging lens. Consider a concave lens and let a ray of light fall on the lens. Let us see how this light ray refracts. When the light ray travels from a rarer medium to a denser medium, the light ray bends towards the normal, and when this light ray travels from the denser to a rarer medium, it bends away from normal. Now if I extend this refracted ray, I find that it passes through the focus. Therefore, a concave lens diverges a parallel beam of light falling on it. Thus we can call a concave lens as a divergent lens. Thus, we have seen a ray of light parallel to the principal axis after refraction from a convex lens passes through the principal focus, and in case of a concave lens, the ray appears to diverge from the principal focus. Now consider the case when a light ray passing through the focus strikes the lens. This ray after refraction is going to become parallel to the principal axis. Similarly, for a concave lens, a ray of light which is directed towards the focus after refraction from the concave lens will appear parallel to the principal axis. Thus we can say a ray of light passing through the principal focus after refraction from the convex lens will emerge parallel to the principal axis, and a ray of light appearing to meet the principal focus of a concave lens after refraction will emerge parallel to the principal axis. A ray of light passing through the optical center of a concave lens will emerge without any deviation And similarly, a ray of light passing through the optical center of a convex lens will also emerge without any deviation. Now once we are clear with this, let us see the ray diagrams for objects placed at various positions in front of a convex lens. First, let us start when the object is kept at infinity. The light rays emerging from the object will be parallel rays striking the convex lens, and we already know that after refraction the parallel rays are going to converge at the focus. Therefore, we get the image at focus f2. The image we get in this case is real, the image is going to be inverted, and the image is going to be highly diminished in size. Now, let us place our object beyond the center of curvature. Draw the first ray parallel to the principal axis, which after refraction is going to pass through the principal focus. Draw the second ray through the optical center, which will pass undeviated. Draw one more ray from the foot of the image, also through the optical center, which is going to pass undeviated. Therefore, the image we get is real, it is inverted and diminished in size. Let us now place our object at the center of curvature and draw the ray diagram. Draw the first ray parallel to the principal axis, which after refraction from the lens is going to pass through the focus. Draw the second ray passing through the optical center, which we know is going to pass undeviated. Draw one more ray from the foot of the image, also passing through the optical center. Therefore, the image we get is real, is inverted, and is of the same size as the object. Now, let us place our object between the center of curvature and the focus. Draw the first ray parallel to the principal axis, which after refraction is going to pass through the focus. Draw the second ray passing through the optical center, which will pass undeviated. Draw one more ray from the foot of the image, also passing through the optical center. We find that our image forms beyond the center of curvature, our image is enlarged compared to our object, and the image is real and inverted. Now, let us place our object at the principal focus and draw the ray diagram. Draw the first ray parallel to the principal axis, which on striking the lens after refraction is going to pass through the focus, and draw the second ray passing through the optical center. Now we find our image forms at infinity. This image is going to be highly enlarged, the image is going to be real and inverted, but the image is going to form at infinity. Now place the object between the focus and the optical center. Draw the ray diagram. Draw the first ray parallel to the principal axis, which on refraction will pass through the focus. Draw the second ray passing through the optical center. On extending these rays backwards, we get the image on the same side of the lens. The image is enlarged, also the image is virtual and erect. The table here gives the summary of the position and the properties of the image corresponding to the position of the object for a convex lens. Now, let us draw ray diagrams for a concave lens. Consider the first case in which our object is kept at infinity. Draw the first ray parallel to the principal axis, which after refraction from the concave lens will diverge. Draw the second ray in the same fashion. Now, when I extend these rays backwards, these rays meet at the focus. Therefore, I get my image at the focus, which is highly diminished, point size, and the image is virtual and erect. Now, consider the second case in which our object is between infinity and the optical center. Let us draw the ray diagram for this case. Draw the first ray parallel to the principal axis, which after refraction from the concave lens will diverge like this. Draw the second ray through the optical center, and we know that this ray is going to pass undiverged. Now if I extend the first ray backwards, it is going to meet this ray at this point. Therefore, the image I get is going to form between the focus and the optical center, and this image is going to be diminished. Also, it will be virtual and erect. This table shown gives the summary of the position and the properties of the image formed corresponding to the position of the object for a concave lens.
So let us quickly recap what we learned in this lesson. We got acquainted with the terms used in lenses, and we learned to construct ray diagrams for both convex and concave lens.